thank you, everyone, and thank you for inviting me to give this talk. I'm very excited to be here. So I assume that most people, if not all of you, have heard about large language models like ChatGPT. Just in case you're not familiar with them, it's a computer program. You talk to it; it talks back to you. I asked it to send a greeting to you. I am not going to read it because I don't do a very good pirate accent. But that's what ChatGPT had to say to you all. ChatGPT's garnered a lot of attention since it was released about a year and a half ago. Large language models have been around for a little longer than that, but it was ChatGPT that really got the public attention. And reactions to ChatGPT have completely run the gamut. Some people say it's just like a stochastic parrot, and some people say we're seeing the sparks of artificial general intelligence. And so I'd like to start off by giving a little history of reactions to artificial intelligence, because this wide range of reactions is really nothing new. And I'd like to talk about two effects that observers of artificial intelligence have talked about, two opposite effects. One's called the Eliza effect, and one's called, somewhat generically, the AI effect. So the Eliza effect is named after, the Eliza effect was a term coined by Sherry Turkle at MIT, and it's the general tendency to treat responsive computer programs like ChatGPT as more intelligent than they really are. It's named after the very first chatbot, which was named Eliza. Eliza was named after Eliza Doolittle. And here's an example conversation. This was written in 1966, and this is a picture of the creator, Joseph Weizenbaum, also at MIT, talking to it, I guess, in some very, very old-looking teletype machine. So the conversation is like this. The human operator types in caps and lowercase, and the program writes back in all caps. So men are all alike. In what way? They're always bugging us about something or other. Can you think of a specific example? And so on and so on. And it's a kind of a reasonable conversation. It was meant to simulate a certain kind of psychotherapist, a Rogerian psychotherapist. Actually, some of you probably have some psychology background and are familiar with that school of psychotherapy. And it was supposed to simulate kind of a therapy session. And it's a pretty good conversation. This was the example conversation from the original Eliza paper. And one of the things that Weizenbaum found very striking when he first created this program was the way that people reacted to it. He was quite surprised, even shocked, to see that people talked with Eliza as if Eliza was a real person. And the most famous anecdote from him was this one. My secretary watched me work on this program over a long period of time. One day she asked to be permitted to talk with the system. Of course, she knew she was talking with the machine because she'd watched him create it. Yet after I watched her type in a few sentences, she turned to me and said, "Would you mind leaving the room, please?" And so the point of the story is that she knew exactly what she was talking with, and yet still somehow she felt that she needed to talk about something very personal with this virtual psychotherapist. So the Eliza effect. People saw it and thought, wow, this is a really amazing conversational agent. But if I tell you a little bit about how it works, and you may have a different opinion about Eliza. So the way that Eliza works is it has a bunch of rules that look like the ones here. Does this actually work? No, I don't know. It has a bunch of rules like the ones that you see here. So if you type in something like "I need some help, that much seems certain," then that will fire a rule that says X, I need Y. If it matches that pattern, then it will apply one of the things to the right-hand side of the arrow. All right, so if you say X, I need Y, then that will match against the thing that you wrote up there. So X is blank and Y is some help. And so it'll just come back with the thing to the right of the arrow, which is what would it mean to you if you got some help. If you type the same thing again, it'll say, why do you want some help? If you type the same thing again, it'll say, suppose you got some help soon. And these are all very reasonable sounding responses, but you can see that they're just canned responses that are formed by finding a keyword in what you say and then maybe cleverly cutting and pasting some things out of what you said and echoing them back to the user to produce a fairly compelling kind of result. Does it make sense? Yeah, so I hope it's not a controversial thing for me to say that this is not a genuine conversation. This is not what we do. This is not natural language understanding. This is not what we do when we have a conversation. And most people, if they see this, will agree and say, oh, it's not as intelligent as it seemed at first. Okay, so this is the Eliza effect. Is if you just use the thing, then you might think it's very intelligent, but now you're experiencing the opposite effect, which is when you see how the innards of the machine work, then your opinion of its quote-unquote intelligence will decrease, and that's the opposite effect, which has been sometimes called the AI effect. Maybe the mild version of the AI effect is when you understand how the system works, then your estimation of its intelligence may decrease. Put in a slightly more extreme, somewhat sarcastic way, Larry Tesler said that the AI effect is intelligence is whatever machines haven't done yet. I think the most prominent example of the AI effect, at least in my memory, was in 1997 when IBM built a computer called Deep Blue that defeated Garry Kasparov, who at the time was the reigning world chess champion, in an actual official tournament setting of chess. They played, I don't remember how many games. Kasparov won some, but Deep Blue won more, and Deep Blue won the whole match. And this was a major event because it was the first time that computers had beaten the best human at something that we have long considered to be a hallmark of human intelligence. And it was a big deal, and people said things like this. While nobody could have known at the time, this was the moment when machines truly began their conquest of Earth. So, very exalted kind of language used to describe this kind of computer, but when a lot of people started to understand better what was going on inside Deep Blue, their estimation of Deep Blue kind of changed. Deep Blue was a pretty amazing machine, even by today's standards, had 30 CPUs, 480 custom-built chess chips, had a database that included 700,000 complete games, all possible endgames with 5 or less pieces, and it was able to search 200 million positions per second. So in these respects, actually, it far exceeds current chess computers, although current chess computers play much stronger chess. These are amazing statistics. But when people saw this, they said, oh, that's not how I play chess. That's not how Kasparov plays chess. This is not intelligence. This is brute force. And so I think this was one of the most visible manifestations of the AI effect, that people at first thought this computer is going to take over the world, and then they realized how it worked, and they said, oh, well, that's not intelligence. That's just a machine brute force. So that's an example of the AI effect. More succinctly, Douglas Hofstadter was quoted in the New York Times as saying, I used to think chess required thought. Now I realize it doesn't. Unsarcastically, yeah. So this is another way of expressing the AI effect. So we have these two opposite effects. The Eliza effect causes us to superficially treat a system as being more intelligent than it really deserves to be, and the AI effect is the opposite effect. And the AI effect causes us to think of a machine as less intelligent than it deserves to be. And we don't want to commit either mistake. We want to have the exact right estimation of what machines really are. And both sides of this needle are widely regarded as being intellectual fallacies. And even if the correct position is that it's not possible for machines to have intelligence, which is, I think, a position that probably a lot of people in the room hold, it's not just something that you can just assume as a knee-jerk reaction. You can't just say it's a machine, therefore it can't be intelligent. This is a position that actually needs to be justified, and we have to have good reasons for believing this. So these two opposite effects are both things that need to be we need to be cautious of. The difficulty of managing this tension between these two effects is that our yardstick for what intelligence is of course, ourselves. And as we've already seen from some talks this morning, we don't always completely understand what it means when we say that we're intelligent either. The mind and the brain are both are somewhat mysterious to us. And increasingly, we do not know what happens inside the models that we create either. Something like Deep Blue, something like Eliza, everything was programmed by hand. We understood how it all worked. Increasingly, as machine learning dominates these methods, they produce these large matrices of weights, and we don't necessarily know what happens inside them either. And so it becomes more and more difficult for us to say, oh, I understand what the machine's doing. That's different from what I'm doing, because my powers of introspection are not perfect, and my powers to interpret the models are also not perfect. So this is a difficult question, a question that I do not claim to be able to answer today. What I do know is going to be helpful is always, it's a good thing for us to understand better the things that we're talking about. So this is kind of my agenda for my talk today. I would like to talk to you about language models and help you to understand better how language models work, hopefully demystify them a little bit, and talk a little bit about what they're capable of doing and what they're not capable of doing. And the examples that I've selected of what language models cannot do, there's a lot of things that researchers talk about and people discuss. I've selected particular examples of limitations of language models where we actually do know pretty clearly what's going on inside the model. And to a large extent, we do know pretty clearly what we're doing when it comes to these things. And we are able to say pretty confidently that what these language models are doing is different from what we're doing. And so I like these cases because they're more clear-cut, and they're good examples of how wide the distance can be between the perception and the reality of a large language model. It may appear to be so good at having a conversation, but the reality is sometimes there are some pretty serious limitations. All right, so that's the outline for the talk today. So what is a language model? One of the oldest papers about what we would now call language modeling actually studied human ability at language modeling. So let's play a game. It's now called the Shannon game. Claude Shannon was the founder of information theory. So the game is to predict the next letter. Letter or space, so both letter and space count as characters. I've given you the first letter, and there's a right and wrong answer. So can you all guess what the next character is? Very good. Okay, the next character is H. Okay, what's the next letter? E. Very good. What's the next character? Space. Okay, what's the next character? C. I heard someone say R. Yes, it's R. Maybe you've read the paper. The sentence comes from the paper. Okay, what's the next character? I. No, it's O. I don't think I heard anyone say O. It's another O. Okay, I heard a lot of M's. It's M. Okay, what's the next character? Space. I. No, it's W. You were quite certain that it was I, but it was actually W. A. S. Space. I. C. O. T. F. I. I heard someone say V. E. R. Y. Space. B. C. S. A. G. H. Okay. All right, you all did pretty well. So did you notice that sometimes did you all notice that sometimes you were quite unanimous about what the answer was, and very often you were right, especially like if you saw a complete word, then you guessed the space. If you saw when it was right off the bat, it was a T, and you just know that a lot of English sentences start with the, and so you were pretty sure that it was an H. At some points in the sentence, you were quite uncertain about what the next character would be. But as you were doing this, you were relying on your knowledge of English spelling, English grammar, the kinds of things people normally talk about, and you were relying on various aspects of your knowledge of English and just your knowledge of the world. Does that make sense? Okay, so Shannon actually measured like how well his wife was able to do this prediction task. Okay, so another very old example of a language model is called a bigram language model, also known as a Markov chain. That's Markov. So if you have this model and you want to train it on some text, so the training text is ba ba black sheep have you any wool, then you can build this very simple model on the lower right where you have a matrix, and each matrix says what's the probability of the next letter given the previous letter. All right, so there are 7 A's in this text, and 2 of them are followed by another A. So that's why the probability of A given A is 2/7. Does that make sense? Okay, so you can train this very easily. You can write a Python program to do this very quickly, and you can train this on a bunch of text. You've got your model. Then you could use this model to play this game, or you could use this model to try to generate random sentences. You could try to have a conversation with it. You could write a question, and then you could ask the model to try to complete this. And this is a very simple example of a language model. All right? So a language model's job, yes?
Is it good to use a song for training data?
Oh,
or would it be better to use something?
I chose this just because it has 2 consecutive A's in it. That's the only reason I chose this example. Because I didn't want to write like A through Z on the matrix. I wanted there to be something non-zero in that upper left corner. Yeah. All right, so 2 examples of language models. You can act as language models when I ask you to play this game of predicting the next letter. And a bigram language model also is a language model. Its job is to predict the next letter. Okay, so that's all a language model is. It's a statistical model whose job is, given some letters or words, to predict the next letter or the next word or the next piece of a word. All right? And so a large language model like ChatGPT is an example of a language model. It's just much, much more complicated than the simple matrix that I showed you on the previous slide. All right, here's kind of a cartoon diagram of how it works. The details are not too important. I will come back to some of these details later. But if you feed in some words at the bottom, amidst the rolling waves and salty air, A, then its job is to predict the next word, and it thinks that Marvel would be a nice completion for this, for these words. All right, so I put the word just in scare quotes because sometimes people kind of want to minimize the significance of language models, and they say language models just predict the next word, and it's true. That's all their job is to do, is just to predict the next word. But let's think about, well, what does that entail? You've already seen that predicting the next letter entails quite a bit of knowledge about English spelling, English grammar, maybe even some knowledge about what kinds of things a room can be or not be, or things like that. So one thing that language models can do is they can write poetry. So if you give it an incomplete poem, it'll make the suggestion for what it thinks the most poetic next word of the poem will be, if it recognizes that you've started to write a poem, or if you've explicitly asked it to write a poem. And so if you just keep guessing the next word over and over again, then a poem will come out. In this case, it's definitely a better poem than I could write. Might not be one for the ages, but it's definitely better than what I can do. Language models can solve math and science problems. So if you give a problem like this, which I will definitely not try to read, it's a complicated question that has a single numerical answer, and the language model has guessed 8. Probably someone in the room knows what the correct answer to this question is. I do not know what it is. But here, guessing the next word, in order to actually guess it correctly, requires some fairly sophisticated knowledge of, this is organic chemistry, right? Organic chemistry, right? So it's not just, it's more than just being able to spell well. You actually have to know some organic chemistry in order to just guess the next word. All right, language models can also play chess. You can just give it a whole string of chess moves and say, this is the beginning of a chess game. Can you tell me what the next best chess move is? All right, in this case, it's guessed bishop to d3, which is it's a legal move, which already actually honestly impresses me. It's not the best move, but in order to guess the best next chess move, you have to be a grandmaster at chess. So just guessing the next word involves much more than just knowing that H comes after T. You have to be a grandmaster at chess in order to make the best possible completion. Does that make sense? Yeah, so sometimes people want to denigrate language models, they just predict the next word, but actually they can do a whole lot. And those of you who have used ChatGPT know that it can do a whole lot with this one power that it has to be able to predict the next word. All right, any questions? Yeah.
I am an organic chemist.
Okay.
So I was reading that most of organic chemistry is done with the symbolic language of unit structures.
Yes.
So
the newest ones can. You can put in images, and then they have another part of the model that can do some image processing. Yes, but I'm focusing on just the symbolic. Yeah. Yeah, thanks. Any other questions? All right. Okay, so what can't language models do? And I said at the outset that I was interested in abilities / limitations of language models where we actually do have a pretty clear idea of what's going on in the model and what's going on with us. So I offer here not a definition of a conversation, but some things that I believe are essential to a conversation. And I hope this is uncontroversial. A conversation includes two agents, two participants in the conversation, with some kind of internal state. Each one has some kind of internal state, and there might be some shared state between them. And words are exchanged between them. So I don't think this is a definition of conversation, but I think that these are all essential. If you're missing these pieces, I don't think it really qualifies to be called a conversation. Does that sound fair? I'm not a philosopher of language. This is just what I think. By contrast, a language model's training data and the structure of the model itself is designed to model a continuous stream of words. And it could be a very, very long stream of words, but its job is to predict a stream of words. And that is not the same thing as a conversation. And the differences between these two things, I think we will see in the following slides, lead to some problems in how language models work. Okay, first problem. This difference between there being two agents in a conversation and they have words exchanged back and forth versus the language model's training data, which is largely newspaper articles, encyclopedia articles, and things like that. It's mostly not conversational. So if you just take the language model that I showed you the picture of with the dots and the lines, and you just train it on a pile of data, like a trillion words of data, then you get just the bare language model. And if you run like ChatGPT in developer mode or something, you can access these language models. So this particular one's called DaVinci 002. It's kind of an older one, but it's one of these language models that has just been trained on the raw text. And if you ask it something like, could you help me write an email to my professor asking for an extension, then it does not answer the question. What does it do? It just goes on, it just continues as if it was a monologue, and it just goes on explaining why this person needs an extension. I have a paper due this Friday. I'm working on it right now. Alas, my computer's having problems booting, and my professor doesn't offer extensions. Why? Because that's a very reasonable continuation of the question. Of course, if two people did this and one person asked a question and the other one started continuing the question, that would be a very odd thing to do, right? But because of the structure of the model and the way it's trained, this is actually a very reasonable thing. So in order to build ChatGPT, they had to do something extra in the training process of ChatGPT. It's called reinforcement learning with human feedback. And what they did was they didn't just train it on a pile of text. They actually had people interact with the system. So they would, the person would give it a prompt like this: could you help me write an email to my professor asking for extension? And the model would generate two responses. And if you imagine the two responses were, I have a paper due this Friday, I'm working on it right now, and the other response is subject, request for extension on assignment due date. Then the robot's supposed to stand for ChatGPT. Then the human would read these two responses and say this one, the bottom one is better than the top one. Repeat this process for I don't know how many times, a lot of times, and this feedback gets put back into the model, and the model learns what kinds of responses the humans preferred more. Alexander will be talking later about the human side of this and what went into this process. So after this process, now the language model, which you can see at the bottom, is GPT-3.5 Turbo Instruct. The Instruct is the original paper that described this process. If you ask it, could you help me write an email to my professor asking for an extension, then as desired, you get the response you get is the actual assistance that you asked for. Okay, but it's still the same model. It's still exactly the same model before. Nothing fundamental has changed. It's just some feedback has been given to make it more conversational. But still, at root, all it's doing is just taking the text that you give it and extending it out. And there's, in my mind, these are two very different kinds of situations where you have to complete a monologue versus you actually have an actual conversation, but nothing fundamental has changed. It's just it's difference in degree rather than in kind. And sometimes the cracks show. So if you put it into a situation where the user and the computer are playing equal roles, then you can actually play some mind games with it and get it confused. So you can say, let's play 20 questions. You think of an animal, I'll ask you yes, no questions about it. ChatGPT says, sure, that sounds like a fun game. Go ahead and start asking your questions. So ChatGPT understands the game. Okay, so I start right off by saying, no, it's not a mammal. So a normal person would say, what? I thought you were going to ask the questions, but ChatGPT is just fine. Got it, it's not a mammal. Is it a bird? So it immediately takes the role of the questioner. Okay, now it gets worse, Then I answer, yes, it lives on the Upper Peninsula of Michigan and the southern tip of Ontario. ChatGPT says, is it a bird of prey? And I say, is it Kirtland's warbler? And ChatGPT says, yes, you got it, it's Kirtland's warbler. So it's confused about who is who in this conversation. Why? Because the model inherently doesn't have any notion of like me and you. It's just completing a string of text. And the reinforcement learning has caused it to be a good conversationalist, but yeah, not always perfect. Okay, second thing. So I claim that a conversation involves some kind of internal state. There are words exchanged between us, but we're also thinking some things that are not necessarily spoken out loud. Right? I think this is something important in a conversation. And so continuing on the 20 questions theme, it's kind of a favorite example of mine. I asked it, let's play 20 questions. Please think of an animal. I'll ask you yes, no questions about it. It says, sure, I'm thinking of an animal now. And I ask it, is it a mammal? And now the computer claims that it's thought of an animal. And its next job is to answer yes or no. Right? Okay, so I claim that GPT is lying at this point. it says, I'm thinking of an animal now, but it is not. It is not thinking of an animal at that point. That is a lie. Why? Because its job is to look at these words. I'm thinking of an animal now, is it a mammal? And to predict the next word. But at this point, when it says, I'm thinking of an animal now, there's just literally no place in this picture for that animal to be stored. Like, it's just looking at words and generating the next word. There's no extra memory cell where that extra piece of information could be stored. All right, so there's no philosophical debate here about, oh, we can't look at the state of mind or anything. No, we can look at the state of mind of the machine right here. Sorry, that's not the state of mind. The state of the machine right here. And we can see that the state just does not have any memory location where that animal can be stored. Okay, and you can also run the language model in a mode where you can actually get it to output what the probability distribution of the next word is. So at that point in time, when I ask it, is it a mammal? It's saying 70% chance the answer is yes, 30% chance the answer is no. So it is deciding these questions on the fly. Does that make sense? Okay, we can continue. I say, I give up, what is it? And it's thinking 27% chance it's a tiger, 19% chance 13% chance it's a bear. That's a giraffe. There's some word splitting that happens. We would call this cheating, right? Sometimes little kids do play it this way, but we would say, like, you know, the fact that it claimed I'm thinking of an animal now was simply not true. Okay. But we know when adults play this game, we know that we truly are thinking of an animal, and I think that's not a controversial statement, that we have enough introspection to know that we're thinking of an animal and that we're staying faithful to the animal as we go through the game. But this is something that the language model just flat out is not able to do. Okay, does that make sense? All right, third thing, I claim that in the conversation there's some kind of a shared state that happens in the conversation. Otherwise, the conversation would not be coherent, and people would not be able to make progress in the conversation because there has to be some kind of a shared state. And in principle, the language model should be able to keep track of this shared state, because unlike the animal, which is inside your mind only, the shared state is there in the history of the conversation. And so it would seem like, based on what we know about language models, they've given some history of words and they're supposed to predict the next word. They should be able to reconstruct whatever state there is from those words. Okay, but it happens to be the case that the particular kind of architecture that is used in ChatGPT actually has a limited ability to track even this kind of state. It's not hidden, it's there, it's plain to see, but actually the model has a limited ability. So if we ask ChatGPT to play this game, I have two cups labeled A and B. When I say S for swap the first two cups. When I say P for pass, don't move any cups. Then please tell me if the cups are in order. All right, does the game make sense? Okay, so if I say swap, then I've got the two cups, I swap and I swap. The cups are in their original order, so it says yes. Does it make sense? Okay, and the language model understands the game too, correctly answers yes. Okay, if I say swap, pass, swap, pass, swap, then the cups are not in the original order, and the language model correctly answers no. Okay, now if I say swap, pass, swap, pass, swap, pass, swap, they are not in the original order, but the language model says yes. Okay, and so generally speaking, if you have a small number of moves, the language model is able to do this. If it's as the number of moves increases, then its ability to do this kind of breaks down. My experience is usually at around 6 or 7 moves, or 6 or 7 swaps, it starts to get a little fuzzy. Okay, yes?
Does it then go back to just the probability of a yes or no answer?
You should be able to inspect the probability here. So I don't know, actually I've never done it. So I'm guessing here this was like no 60% and yes 40%. And then here it got so close to 50 that it started to get kind of noisy. Yeah. Okay, so let's go to the next level and say I have 5 cups labeled A through E. When I say S, swap the first 2 cups. When I say C, move the first cup to the last position. Then tell me if they're in order. Okay, so swap, it says yes, that's good. If I say cycle, it says yes. Does it make sense? We're just going to do this rotation here. So if you cycle 5 times, you'll end up in the original order. If I do 4 cycles, it says no. Okay, so far it's doing really well. If I do swap, and then 5 cycles, and then swap again, now it gets confused. It says no. Even if I do something as simple as SCS, swap, cycle, swap, then it'll say yes, right? But you can picture in your mind's eye that if you swap and then cycle and swap, it's going to be all scrambled up. All right, so 5 cups, it's harder for you too, right? 5 cups is not easy, but it becomes extremely hard for the computer to do. So what's going on here? This is a picture I showed you before. it's got a sequence of moves, and it has to predict a yes or no answer. And the width of this diagram is just how many words there are in the history of the chat. But the height of this diagram is something fixed. So when they created the model, they decided there were going to be 4 or 128 layers or something like that. But that number is fixed. Okay? So if I tell you swap, 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 pass, 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 swap, 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 and if I do it slower, then you listen to the symbols one by one, and you have some kind of state in your mind, or you use your arms or something like that to keep track of the state. The way the machine does this is quite different. It actually looks at all of the symbols all at once, and then it just kind of tries to say that looks odd or that looks even, which is fine if it's a small number of symbols, but it cannot actually sequentially process the symbols the way that we do. And this is just a fact about this particular model. Yes?
So this computer cannot count S's?
No.
I mean, I'm thinking
Right.
that's very simple.
Right, and you go left to right, and you could do the counting. Yeah, and so the way it does it, it tries to do the counting all at once.
Okay.
Which you can also do. You can just kind of stare at it, and you can just count it immediately without going left to right. But if I gave you, 23 of them, then you would walk through the string and count them, and then you would ask yourself if it's even or odd. Yeah, so the machine tries to do it all at once, and yeah, the accuracy will get worse and worse as the string gets longer and longer. Yes. Okay, so this is a question that you can actually start to prove theorems about. So it turns out that if you construct the transformer very carefully by hand, you can make it solve the two-cut problem. Most likely, they cannot learn to do it on their own, but if you fine-tune everything, you can probably do it. 3 and 4, I think, are still open questions. With 5, it becomes, under some very mild assumptions, you can prove a theorem that says transformers just cannot do it for 5 cups. Yeah, the fine print is right there. But all of this is rooted in this the property that you saw in the picture, that there's a limited depth to this network, and so its ability to read left to right through the string and track some kind of state in the way that you do pretty naturally, that ability doesn't exist inside this kind of a language model. All right, so those are 3 limitations of current language models that I think are interesting, and there are cases where you can just look at the model and you can see that, like, definitely the language model is or is not able to do this, and I think it's fairly clear in most of these cases that we are able to do these things, and so these are pretty clear-cut differences between how language models work and how we work. And yet people are able to have conversations with it and be amazed by it. And the language model does such a good job of simulating a conversation that these limitations are not always obvious on the surface. And so the difference between the perception and the reality of the language model can be quite wide. So other things that people talk about, factual accuracy, hallucinations are a really big thing that I think Alexander's going to talk about. Problem solving is actually related to the cups. Theory of mind is kind of related to the cups also. Moral and ethical values, these are all things that are widely discussed in the literature. Some of these are a little bit fuzzier and harder to make really crisp statements about. So I've chosen to focus on the ones that are we can really wrap our hands around. But these are all equally important issues that are potentially very serious limitations of language models that people are actively thinking about. Okay, so to wrap up, language models, quote unquote, just predict the next word, but that actually means that they can do some pretty amazing things, like play grandmaster level chess, or, I'm sorry, ChatGPT does not play grandmaster level chess. It plays a very decent game of chess, but not grandmaster level chess. But the ideal language model would be able to play grandmaster level chess, or answering biochemistry questions or things like that. But language models also have some serious limitations. And because they do such a good job at pretending to be what they are, these limitations can be serious while at the same time being very difficult to see on the surface. And so this is the thing that's actually, the kind of the main take-home message that I want you to be aware about. The limitations, the particular limitations I've highlighted here are not necessarily deep or permanent limitations. I expect that they will be resolved in possibly the very near future even. But this question of the Eliza effect and the AI effect and how do we properly assess the intelligence or lack thereof of these systems, and how do we recognize their abilities and limitations, which may differ from our perceptions, these are all questions that we will continue to grapple with for quite some time to come. So thank you very much, and I'll be happy to take more of your questions.